He'll speak on Freudenthal suspension in unstable motivic homotopy theory. Please go ahead.
All right, thanks Inofi, Philippe, and Kirill for the invitation. It's great to be here virtually. All right, so I'd like to tell you a story about the Freudenthal suspension theorem and unstable motivic homotopy theory. I don't expect most people here are motivic homotopy theorists or topologists for that matter. And so maybe I should start by telling you why you might care about any of these things. So I'd like to start with a classical conjecture about projective modules. So suppose K is an algebraically closed field and D is some integer which is bigger than or equal to 1. And suppose I have a smooth affine variety of dimension D plus 1 and a rank D vector bundle on X. So it's a basic question, and I'm going to say much more about this in a few minutes. When does E split off a trivial rank 1 summand? In other words, when can I write E as the sum of a lower rank bundle and a trivial rank 1 bundle? And it's a natural question to ask if I can give explicit conditions which guarantee when that happens. And so Murthy in 97, I guess this was actually published in 99, asked the question, which I've formulated here as a conjecture, which is that there is a necessary and sufficient cohomological condition for guaranteeing that geometric splitting, namely the first obstruction that you could think of, namely the vanishing locus of a generic section is empty, is the only obstruction. So in this case, I've written that as the Dth Chern class of E vanishes. And I'm thinking of the Dth Chern class as lying in the Chow group of codimension D cycles on X. All right, so Murthy asked this question in 97, and basically he said, I know no examples where this is not true. It's sort of immediate that the statement holds when D is equal to 1, in which case it's essentially a tautology. So the first interesting case is when D is 2. So what I'd like to sketch for you today, or indicate how one might prove, is the following theorem, which builds on work of mine with Jean Fazel, which is that this conjecture is actually just true if K has characteristic 0. So I'll give you some history about this problem in a few minutes, but I want to start even more classically. So I'd like to go back in time to the 1950s. So I know there's probably a lot of people here who have questions about torsors, but the moral of the talk in some sense is that Murthy's conjecture here will end up formulating it as a homotopy theory problem. And in order to solve that homotopy theory problem, we're going to want to make some computation, and it'll be some computation of something like a homotopy group. And while that homotopy group is naturally sort of unstable, what's actually computable is something stable, and what we're really interested in is sort of the link between the stable and the unstable. So that's kind of the goal of the talk, to describe that stabilization process. All right, so let me start very classically in the theory of projective modules over commutative rings. And suppose I have a Noetherian ring of curl dimension D and a projective module of rank R. I'm going to introduce a little bit of notation. So I'll write VR of spec R for the set of isomorphism classes of rank R projective modules. And by Serre's theorem, or the Serre-Swan correspondence, or whatever you feel like calling it, Serre's dictionary, this is the same thing as considering vector bundles of rank R over the prime spectrum. And it'll be useful to have one additional integer that we attach to the situation. And that's going to be the co-rank, and that's going to be the difference between the dimension and the rank. So what we'll see is that there are essentially several ranges that we're going to want to consider. And to indicate what those are, let me start with a theorem. So first, one more bit of notation. There's a stabilization function. If I have a projective module, I can always add a free rank 1 module to it. And that defines a map from rank R minus 1 projective modules to rank R bundle modules, and I'm going to, or equivalently, rank R minus 1 vector bundles to rank R vector bundles. I'm going to write SR for that stabilization function. All right, so what can I say about this stabilization function? So maybe the place this got started is in the work of Serre, And what he observed, and this is one way it can be formulated, is that this function SR is surjective for R bigger than D. In other words, in the situation where you have negative corank. So this just means that if you have a projective module of rank larger than the Krull dimension, then it will always split off a trivial rank one sum n. So why was Serre motivated to prove this theorem? Well, there's a corresponding dictionary between vector bundles in topology and projective modules over Noetherian rings. And the corresponding statement in topology, which I'll come back to later, is sort of immediate by a general position argument. And so Serre's argument is essentially an algebraization of this kind of general position argument. And roughly speaking, you're saying that a generic section of a vector bundle is nowhere vanishing as soon as the rank is bigger than the dimension, roughly speaking, because the vanishing locus of a generic section is going to have a codimension which is larger than the dimension. All right. So this theorem, I think, sort of got the theory of projective modules or vector bundles and algebraic varieties off to a running start. And in building on this result, Bass sort of asked this question, which is, can you characterize the image of SR? And this turns out to be a quite difficult problem as soon as the corank is not negative. So let me start by discussing a little bit of the history around this problem about characterizing the image of SR in the first interesting case, which is corank 0. All right, so now why is corank 0 interesting? Well, if I take a suitably generic section of a projective module of rank D, then its vanishing locus is a codimension D subvariety. In other words, generically, it's a finite collection of points. And so there is a non-trivial obstruction to this kind of splitting problem, right? And more generally, that's just the Dth Chern class. So if I look at the cohomology class of that as an algebraic cycle and the Chow group of codimension D cycles, modular rational equivalence, then whether or not that class is 0 is necessary as an obstruction to. So we can ask the question, well, is that obstruction necessary or sufficient? Unfortunately, it's insufficient in general to guarantee splitting. If I work over the real numbers, there's an example due to Swan, which is inherently topological. If you take the tangent bundle of the real 2 sphere, in other words, take the real hypersurface given by the usual sphere, then its Chern class, its second Chern class is 0, but it doesn't split off a free rank 1 sum n. So that's unfortunate. In general, this obstruction is not sufficient, but are there cases when it is sufficient? All right. So there was a lot of work done on this problem in the case when K was algebraically closed, and the end of the story was that if you have a smooth affine variety over an algebraically closed field, then the vanishing of the top Chern class is the only obstruction to guarantee splitting. So in other words, the image of the stabilization map consists of exactly those bundles with trivial top Chern class. So let me say a few words about how long it took to prove this theorem. I haven't attributed it because I'm now going to attribute it to many people. So when D is 2, this was established by Swan and Murthy in the mid-70s. Of course, they all established more. This assumption about smoothness was not quite necessary. There's weaker formulations that are actually true, but for the purposes of this talk, let me restrict to that situation. And in fact, they were interested in cancellation questions for vector bundles, and that kind of indicates what kind of techniques you might imagine using. If you're interested in understanding the stable isomorphism class of a vector bundle, then that's essentially a K-theoretic question. And so then you can try to kind of destabilize by building explicit sort of modular elements and such things. And that's essentially how they were thinking about this. So to move from 2 to 3 took a number of years, and the dimension 3 case was established by Mohan Kumar and Murthy in the early 80s. Again, the techniques are sort of classical K-theory inspired. And so there were some sort of, well, maybe I won't mention what the sort of issues were, but soon thereafter, or relatively soon thereafter, another 12 years later, Murthy established the general case for this result. And as I was sort of suggesting, I mean, these proof uses only kind of classical tools after sort of Bass's analysis of K naught. So then there's this sort of wide open question, which is what happens when K is not algebraically closed? I mean, as we already saw in the case of the real numbers, there is something to be said because the vanishing of the top turn class is certainly not sufficient to guarantee existence of a splitting. And then there are a host of secondary questions. I mean, this is just the first interesting case of Bass's question. What can one say about Bass's question more generally if the co-rank is bigger than 0? So I'd like to talk about that, but in order to do that, I want to introduce some tools from homotopy theory. All right, so let me quickly talk about splitting problems in topology. This is sort of to the point because part of the reason that these questions were studied in algebraic geometry is because they were viewed as analogous to corresponding questions in topology, and those questions in topology had solutions. And so unfortunately, it's not the case that one can simply algebraize the topological proofs, but those techniques are definitely useful. So now I'm going to suppose M is a manifold or something that has the homotopy type of a finite CW complex for concreteness. And I'm going to write, as before, VR for the set of isomorphism classes of real vector bundles on M. Okay. So the basic observation in topology is that this functor is homotopy invariant. If I let I be the unit interval, then if I pull back along the projection from M cross I to M, vector bundles, there's a bijection between isomorphism classes of vector bundles. So granted this homotopy invariant statement, there's a nice way to think about this in purely homotopy theoretic terms. So I'm going to write GR top for the infinite dimensional Grassmannian of r-dimensional subspaces of some infinite dimensional real vector space. And this carries a tautological vector bundle, just the vector bundle which to a given point of the Grassmannian attaches the corresponding r-dimensional subspace. And now if I have a continuous map from M to the Grassmannian, then of course I get a rank R vector bundle on M by pulling back. And by the homotopy invariant statement that I established above or discussed above, if I have homotopic maps to the Grassmannian, then they yield isomorphic vector bundles. And Pontryagin and Steenrod observed in the late 40s that this construction actually determines a bijection from homotopy classes of maps to the Grassmannian to isomorphism classes of vector bundles. All right, so what this allows us to do is it allows us to reformulate a number of those lifting problems in purely topological terms. So first, let me observe that there's a map from the Grassmannian of R-1 dimensional subspaces of some infinite dimensional vector space to the Grassmannian of R-dimensional subspaces, which corresponds to the map which classifies adding a trivial rank 1 bundle to a rank R-1 bundle. And I'd like to ask the question of when a rank R bundle has a nowhere vanishing section. And what I'd like to observe is that this can be phrased, granted the homotopy classification, as a lifting problem. So an equivalent way to phrase this is, well, nowhere vanishing sections are equivalent to trivial rank 1 summands. And so I want to know whether, given a map from M to the Grassmannian of R planes, whether I can lift it along SR to a map to the Grassmannian of R-1 planes. Fortunately, at the same time that Steenrod established this, in his famous book, The Topology of Fiber Bundles, not only did Steenrod and Pontryagin give kind of this classification result, but they gave a host of techniques for analyzing this exact kind of lifting problem. And these things typically go under the name of obstruction theory. All right, so as I said before, there is an evident obstruction to existence of a nowhere vanishing section. And in this case, if I take the point grade dual of the vanishing locus of a generic section, that gives rise to something which I'm going to call the twisted Euler class. Now, let me briefly mention why I say twisted Euler class, because this is the one point at which you can't go back to Milner and Stasheff and say that this is exactly what the situation looks like. It seems to be not as well exposed in the literature. But if I look at the fundamental group of the Grassmannian, then this is actually Z mod 2 via the determinant map. And therefore, if I have a classifying map for a vector bundle, I get a continuous map from M to the Grassmannian, then I get a homomorphism from the fundamental group of M to Z mod 2. And such things are typically called orientation characters. And by the Hurewicz theorem and point grade duality, by the Hurewicz theorem and basically the universal coefficient theorem, these are the things that we can use to sort of twist cohomology classes. So that orientation character Z mod 2 acts on Z and allows me to define a local coefficient system, which I'm going to call Z twisted by the orientation character. And the Euler class naturally lives because of twisted point grade duality in the Deith cohomology of M twisted by this orientation character. And it's it follows sort of by the definitions that I've given on the assumptions on dimension that if I have a topological space which has the homotopy type of a CW complex of dimension D, for example, a manifold of dimension D, then certainly the vanishing of this Euler class is an obstruction, but if you have a manifold of dimension D, then that's actually the only obstruction. All right. So why do we know that this is the only obstruction? Well, if you have a manifold of dimension D, the answer is, well, there's nothing else that you could do. I mean, there's no space, but if you have something that has the homotopy type of something of dimension D, then you have to do a little more work because you have to make sure, well, in essence, the vanishing of the Euler class gives you an obstruction to building a vector bundle up to sort of the D skeleton of your CW complex, and then you're going to have to understand how you can add cells beyond that. All right, so in general, what we can do is we can understand the extent to which this map SR that we wrote down fails to be a homotopy equivalence. And there's a space which sort of measures exactly that. And that space is homotopy equivalent to an R-1 sphere. And a consequence of that is that there's what we call a fiber sequence. So this is actually a Serre fibration. And so if we'd like to analyze this problem of lifting along SR, then what Pontryagin and Steenrod gave us, or re-envisioned after the work of John Moore, is that we can factor this lifting problem into a sequence of easier lifting problems which depend on the homotopy theory of the R-1 sphere. But what's key here is that these obstructions are going to depend on the unstable homotopy of the R-1 sphere. So let me cast the Euler class in that language. So the first non-vanishing homotopy group of the R-1 sphere, and here I'm going to assume R is sufficiently large, for example, bigger than or equal to 2, then the first non-vanishing homotopy group appears in degree R-1, and there's the classical degree map from the R-first homotopy group to the integers. And the Euler class arises from this. So if I look at that sequence there, there's a primary obstruction to lifting, and it is attached to this first non-vanishing homotopy group. All right, so one of the things that was observed in topology is that you can go beyond this. And in the early 1950s, building on the techniques that Steenrod had written down, people started analyzing this splitting problem, for example, in higher co-rank cases. So now, if I have a manifold of dimension D+1, and I have a bundle on X of dimension of rank D, then let's suppose I want to split a trivial rank 1 summand off. There's the evident primary obstruction, which is the vanishing of the Euler class in this twisted cohomology group. But there's a secondary obstruction. And I'm just going to write this down. It's a little bit more complicated. It involves some sort of cohomology operations. W2 of psi is the second Stiefel-Whitney class of the bundle. But loosely speaking, if I have a bundle of dimension or bundle of rank D and the Euler class vanishes, well, the Euler class is some cohomology class and it's given by some homotopy class of maps. If I choose a null homotopy of this Euler class, in other words, something that witnesses that it's vanishing, then there's many possible choices of such things. So if I choose a different, two different null homotopies, then that's going to give rise to some naturally defined cohomology class, because it's going to give you a map basically from some suspension to some cohomology class by gluing the two null homotopies together. And so that is, loosely speaking, where the secondary obstruction comes from. And so that tells you that the secondary obstruction lives in HD plus 1 of M. In order to deal with this issue involving the orientation character, we work with Z mod 2 coefficients. And then there's a question of well-definedness of these of this secondary class. And I made a bunch of choices in sketching where this comes from. Namely, I chose several null homotopies. And if you see how those null homotopies affect the choice of this cohomology class, you see that this is kind of the group in which this construction is well-defined. So that can be phrased in a number of different ways, but loosely speaking, that's the idea of where these secondary obstructions come from. You choose null homotopies of this Euler class, and then you sort of build something that's suitably well-defined out of them. All right, so we know where the primary obstruction comes from. It, as before, comes from the Dth, the R minus, the D minus first homotopy group of SD minus 1. But then there's a question of where the secondary obstruction comes from. And this comes from a bit of homotopy theory. So if I compute the Dth homotopy group of SD minus 1, at least for D sufficiently large, you can do this for D equals 3. This is Hopf's classical computation of the third homotopy group of S2, which we know is generated by the Hopf map, which will make some reappearance later. And I want you to observe two things here. First of all, these groups aren't the same for all values of D. They become constant, namely Z mod 2 for D bigger than or equal to 4. And there's some relation between the various groups. So in the theorem, there was an assumption that D was bigger than or equal to 4, and that was simply to put us in this situation where these groups were all Z mod 2s. There is a version of the statement for D is equal to 3 as well. It's a little bit more complicated, and the description of the secondary obstruction is a little bit more involved. Rather than the Steenrod squaring operation, you'll end up with the Pointryagin square operation, which goes from H2 of M to H4 of M. And you need some integral version of the second Stiefel-Whitney class, but there's a formulation which is completely analogous to this. So the observation is, well, as long as we're in this stable situation, the obstructions that we're going to get are going to be suitably uniform. All right. Any questions so far? So basically, the moral of the story so far is if we want to understand this splitting problem in topology, well, it amounts to understanding the unstable homotopy of the sphere, which is probably one of the most classical problems in homotopy theory. All right, so I'd like to take this analogy between vector bundles and in algebraic geometry and in topology very, very seriously. And now I'd like to basically recast this entire story in the setting of motivic homotopy theory. All right, so I was interested in projective modules over Noetherian rings, and I'm going to need to restrict my attention a little bit to be able to apply homotopy theoretic techniques in this context.
So
Maybe the first
Arvind, you
observation.
said that in topology, the answer is no to this splitting problem.
That's right.
So I didn't quite get what it is
Oh, sorry.
in general.
Oh, in general. Oh, right. So in general, the answer is it's known, but it's hard to write down. And what is the obstruction? I mean, if I want to split off, if I have a manifold of dimension 143 and I want to split off, I want to look at rank 43 bundles or something and split off a trivial rank 1 summand, then I need to know something about, say, the first 100 homotopy groups of a suitable sphere. And there are computational difficulties, at the very least, let me say, to understanding that. So to the extent that we can compute unstable homotopy groups of spheres, there are an inductively defined sequence of obstructions to answering the splitting problem in general. Those obstructions become increasingly baroque as the co-rank increases, as we can already see in this case. I mean, there's a well-definedness issue. The next obstruction is only defined once the previous obstruction vanishes, and determining the indeterminacy of the given cohomology class becomes more and more difficult as you go higher and higher. So maybe I should say that it's in principle solvable. In practice, actually writing down the obstructions can be extremely difficult. And I think historically, people went and understood sort of up to co-rank 3 in great detail. There's some work of Emery Thomas in his seminar on fiber spaces, where I think some of these results are exposed up to that situation. Beyond that case, I think controlling the indeterminacies is only doable in sort of special cases. So for example, there's work of Switzer where he understands sort of this kind of obstruction theory to build sort of rank 2 bundles topologically on projective spaces. And then he can go up to rank 14 bundles or something by sort of a careful analysis of the Postinghoff tower. But this becomes harder and harder. Does that
So is the number of conditions always the co-rank?
That's right.
Or does it depend on where the homotopy groups of spheres are non-zero?
So it turns out that the unstable homotopy groups of spheres are going to always be non-zero in this, but yes, it depends on both of those things, on the co-rank, and if the homotopy group exceptionally happens to vanish, then you would be okay, but it rarely vanishes.
So if it vanishes, then one of the conditions becomes automatic?
Exactly.
Okay, thank you.
Any other questions? All right, so basically the first limitation in understanding this kind of thing is understanding what the unstable homotopy groups of spheres are. And I've already indicated that's a very hard problem, and maybe an easier problem is to understand a suitably more regular situation to the stable situation. All right, so in algebraic geometry, we can build a Grassmannian. I'm going to call it an infinite dimensional algebraic variety. It's a colimit or filtered union of finite dimensional varieties. So maybe you shouldn't call it a variety. But we also know what the functor of points of the Grassmannian is. If I have a map, say, from an affine variety to a Grassmannian, that's the same thing as giving a vector bundle and a collection of generating sections, some number of generating sections. In this setting, I can replace the unit interval by the affine line and speak of naive homotopies between such maps. And I can think about that as just a map from spectrum of a polynomial ring in one variable over R, which has the property when I restrict it to 0 and 1, I get back the maps that I started with. So I state this as a theorem. If I have a field and a regular K algebra, then there's a bijection between what I'm going to call naive homotopy classes of maps to the Grassmannian and isomorphism classes of rank R vector bundles on spec R. So maybe a few comments here. it's not obvious that naive homotopy is even equivalence relation. So a priori, this should be the equivalence relation generated by naive homotopy. But maybe implicit in this statement is something that's extremely non-trivial, which is that if I have a vector bundle on basically the analog of homotopy invariance for projective modules is true, and this is a non-trivial theorem. It's called Lindel's solution to the Bhaskell conjecture in this case. So here K is supposed to be a field or something close to that. So both of these things are actually issues. Naive homotopy is not a good notion. It's not an equivalence relation in general. And as I said, I've swept a very deep theorem under the rug here. All right, so why did I restrict attention to regular rings? Well, this kind of homotopy invariance phenomenon, I mean, the fact that a projective module over a polynomial ring and one variable over some regular ring over a field is sort of pulled back from the regular ring, that is just false, even in rank 1, if we drop the regularity assumption. All right, and so in order to have some kind of homotopy invariance, I need to put some restrictions on the rings that I'm going to consider. So this is the main reason that I'm restricting attention to smooth varieties later. All right, so I'm going to start with K, a fixed base ring, and I'm going to write smooth K for the category of smooth K schemes or K varieties. And if I want to do homotopy theory in this category, well, there's some basic problems. This category of smooth variety is sort of not big enough to do homotopy theory. There's various kinds of constructions that we'd like to perform. For example, we'd like to have the Grassmannian, which is a filtered colimit of smooth varieties. Furthermore, we can't form all quotients and things like that. So in order to sort of do homotopy theory, what we're going to do is enlarge this category. And following Grothendieck and Blavatsky, there's kind of a standard way to do this. We'll take smooth schemes and embed them via the Uneda embedding in some category of presheaves. And because we want to have some homotopy theory intrinsically, I'm going to embed them in special presheaves. Now, it doesn't matter too much. I mean, there's lots of different choices for what spaces can be, but basically what you should take away is that spaces is some enlargement of the category of smooth varieties where I can perform various operations. In particular, I can form limits and colimits. Now, if I pass the simplicial presheaves, then I kill, or maybe how should I say this? While this category does have all limits and colimits, it doesn't preserve the colimits that already existed. So for example, if I have a variety and I can glue it together out of 2 open subschemes, that's a colimit, but it's not a colimit that's preserved when I pass to simplicial presheaves. So in order to make sure that I remember some of the colimits that I already had, I'm going to force some maps to be weak equivalences. So first, I'd like to force things that are Nisnevich locally true or Nisnevich locally weak equivalences to be weak equivalences. So if I have some variety and I can cover it by some open cover UI, where by an open cover here, I really mean a Nisnevich cover, then I can build a check object out of it, which is just given by taking iterated fiber products of the various pieces. And what I'd like to do is force that map from the check object to X to be an isomorphism. So this amounts to forcing, to maintaining or keeping some of the colimits that already existed in the category of smooth varieties. In particular, it imposes sort of Nisnevich gluing. All right, so I'm going to invert those maps. The choice of the Nisnevich topology, I mean, there's various choices of topology, and Nisnevich topology is just useful from the standpoint of some of the things that allows to be true. Maybe for later use, I'll just observe that the Nisnevich cohomological dimension of a scheme is equal to its curl dimension, and like the Étale topology, if I have a smooth variety, then locally in the Nisnevich topology, it looks like an affine space. All right, so the second thing I want to do is just like in classical homotopy theory, I want to force the affine line to be contractible, so, or the unit interval to be contractible in topology. So I want to take the product map x times a1 to x, and I want to force those maps to become isomorphisms. So basically, I'm going to take the category of spaces, and I'm going to invert these two classes of maps. So I'm going to write H algebra of K for the category obtained by inverting Nisnevich local weak equivalences, and H mode of K for the category obtained by inverting Nisnevich and A1 weak equivalences. And this is the Morel-Vygotsky A1 homotopy category. All right, so the technical details aren't going to matter so much, but one of the basic first lemmas that one proves to show that this is a reasonable thing is that if you look at maps in the motivic homotopy category from X to the rank 1 case of the Grassmannian, namely infinite projective space, then this is just the Picard group for any smooth scheme. Unfortunately, this fails in general. And the reason for this is essentially because even if I'm working with regular varieties, the functor of isomorphism classes of vector bundles is not A1 invariant on all varieties. The only A1 invariant statement I've made is for affine varieties. So there's a fix to this, which I don't want to focus on too much, but if at least K is a field or Z, if I restrict my attention to affine varieties, then just like in topology, the Grassmannian represents algebraic vector bundles. And from a concrete standpoint, maybe the way to say this is that the maps in the A1 homotopy category between spec R and the Grassmannian are the same thing as the naive homotopy classes that I described before. So this is a sort of a very special situation. In general, this homotopy category was defined as some kind of localization. So the idea that you could compute maps by some naive point of view is kind of surprising. So this is a non-trivial fact. All right, so this representability theorem was established by Morel in 2006, at least in the case where R is not 2 and K is a perfect field. It's kind of strange assumptions. I mean, we hopefully care about the case R equals 2. I think rank 2 bundles are particularly interesting. And in 2015, Marco Schlichting improved on Fabien's results and dropped the assumption on R. He removed one of the technical ingredients, but couldn't remove the other, and that is why the assumption K perfect is there. But I mention these only because none of those conditions are actually necessary. And in 2015, Marco Ewa and Matthias Wendt and I gave a basically self-contained proof of this. And in essence, what we prove is that the representability theorem is equivalent to the Basque-Quillen conjecture for all smooth algebras over K. So the theorem, as stated above, is reliant on the Basque-Quillen conjecture, and it's stated that way because these are the cases in which we actually know the Basque-Quillen conjecture. So in the case K is a field, this is Lindel's solution of the Basque-Quillen conjecture in the geometric case, and in the case where K is Z, then this is Popescu's improvement, maybe using Swann's redaction of it. So in topology, the other thing that was really useful was that we had these fiber sequences. And in the algebra geometric setting, we also have these kinds of fiber sequences. And so there's a host of people who have thought about fiber sequences in algebraic geometry. Fabien Morel, his student Lucas Fabian Moser, Matthias Wendt thought about this. And this builds on a lot of work of Charles Resk. And then in joint work with Matthias and Marco Ewa, we gave this version of the theorem. Again, there's nothing to this theorem beyond the representability theorem and sort of the general machinery of homotopy theory. So the fundamental difference here is that here we have a fiber sequence in A1 homotopy theory, and we can actually identify the homotopy fiber of this stabilization map in terms of something that looks like a sphere, namely affine space with the original node. All right, and so one can build a version of obstruction theory in A1 homotopy theory. That's largely formal. I mean, Fabien does this in his textbook, A1 Algebraic Topology over a Field, and it's one of the appendices. And so in order to use this for something, we need information about the motivic homotopy type of AR minus the origin. So we've essentially reduced this splitting problem, at least in the case of affine varieties, to understanding motivic homotopy theory of these AR minus the origins, and then being able to compute cohomology with coefficients and whatever those objects are. As you might expect, the situation in algebraic geometry is considerably more involved than in topology. All right, so let me now tell you the story about splitting vector bundles in the motivic setting. All right, so in motivic homotopy theory, there are two circles, and this is different from classical homotopy theory. So when I built the motivic homotopy category, I had this implicit simplicial direction, which has its own sort of internal homotopy theory. In particular, there's a circle which comes from that simplicial direction. One model of that circle, which I'm just going to call the simplicial circle, is the affine line with 0 and 1 contracted. All right, so that is the same thing as the nodal curve. But there's a second circle, which is GM. If you've thought about equivariant homotopy theory, then this is probably familiar. All right, so these spheres that I've just described are linked to things like affine space with the origin removed and the projective line. So the projective line is S1 smash GM, and affine n space with the origin removed is Sn minus 1 together smashed with n copies of GM. So these facts aren't too difficult to prove, but let me skip over why this is true. For the purposes of this talk, let me just observe that an plus 1 minus the origin is p1 smash an minus the origin, all right? So there's one further issue, which is that in this motivic setting, since we were working with simplicial objects and simplicial presheaves, the weak equivalences aren't detected by homotopy groups. They're detected by homotopy sheaves. And so the cohomology that's going to arise in our obstruction theory problem is Nisnevich cohomology with coefficients in these homotopy sheaves. All right, so this is just natural from the standpoint of the Whitehead theorem. While there are two spheres that I've described up there, or two circles, S1 and GM, and this gives rise to a bigraded family of spheres where I smash together all these S1s and GMs, only the simplicial direction ends up being sort of important. I mean, the simplicial direction is enough to detect weak equivalences. This distinction is something that I'll come back to later, and it's sort of important, but let me leave it at that for the moment. Okay, so let's compute. There are a few very fundamental theorems in this subject. Maybe the first one is, most of them are due to Fabien Morel. The first one is that if I look at an minus the origin, then it's n minus 2 connected from the standpoint of motivic homotopy theory. So what does this mean? I mean, I've defined some abstract homotopy theory for you. What concretely does this mean? So what does it mean, for example, for n minus the origin to be A1 connected? Well, the intuition is that if I can connect 2 points by a chain of affine lines, not just over the base field, but over any extension of it, then that will be sufficient to guarantee that it's connected. And you can imagine using sort of configurations of lines to build loops, more complicated versions of connectedness. And at least for the affine, for punctured affine space, that intuition is sufficient. So if I have a chain of 3 lines, which gives me a loop, then you can imagine trying to write an affine plane that fills that in to give you a null homotopy of those loops. And that's what it would mean for a space to be one connected. Every loop can be filled into sort of a 2-simplex in some sense. All right, so for an minus the origin, I hope that connectivity is something that sort of makes sense. Imagine connecting things by lines and such things. All right, so this connectivity statement is analogous to the connectivity of the real points. If I take an minus the origin over the real numbers and I evaluate it on the real numbers, then I get Rn minus the origin, which is homotopy equivalent to the n minus 1 sphere, which is n minus 2 connected. So the next fundamental result is Morel's computation of the first non-vanishing homotopy sheaf. And here we're going to see one fundamental difference. So the analogous computation in topology would be the n minus first homotopy group of Sn minus 1, which is always Z. All right. So it's not going to matter whether you know what the sheaf Milnor-Witt Kn is, but what's important is that it depends on n. And this was reflecting the fact that An minus the origin had these n GMs in it. So there's sort of a weight which now appears. So the vague idea of the proof of this fact from Fabien is that just like in topology, there's a relationship between homotopy and homology, and one can try to compute homology. So there's a Hurevich theorem which links this n minus first homotopy sheaf to a corresponding homology sheaf. And then there's a suspension isomorphism which identifies the n minus first homology sheaf with the zeroth homology sheaf of some discrete space. And loosely speaking, if you have the zeroth homology of some space, then that's the free abelian group on the connected components. And so roughly speaking, this theorem proceeds by describing what the analog of the free abelian group on basically the n-fold smash product of GM is. All right. So this is a homological statement, and that's maybe the key point that I want to make. And Fabien actually gives an explicit description of this free sheaf in terms of generators and relations. I realize that sounds funny when you say the free object and then you say generators and relations, but with an appropriate interpretation of the word free, that actually makes sense. All right, so granted Fabien's theorem, there is indeed a well-defined primary obstruction. So you just run this obstruction theory machine and the first non-vanishing homotopy sheaf gives rise to some obstruction. Just as before, there is some small twist which comes from the analog of an orientation character. And this is the analog of an orientation for a vector bundle. If I have a vector bundle, then its determinant need not be trivial. And so I have to keep track of that failure of triviality. And what I get is a cohomology class in HD of whatever my variety is with coefficients and whatever the sheaf is suitably twisted. In this case, this ends up being a what's known as a Chow-Witt group. And the machinery of obstruction theory tells me that the vanishing of this class is sufficient to guarantee that E splits off a free rank one on that. Now, there have been a host of approaches to obstruction theory in this context, and I'm unfortunately going to skip most of them. There's work of Nori and Bhattacharya Srinivasan, and all of those approaches actually end up being equivalent to this one after a fair amount of work. All right, so what made these computations work in topology? Well, I mentioned before that there was a stabilization that occurred. So taking loops, in other words, maps from S1 into a space, and suspending a space are adjoint to each other. And so there's a unit map for this adjunction. And a classical theorem of Freudenthal is that the unit map of this adjunction in the case of the sphere induces an isomorphism on homotopy in the range that I've written here. So in particular, there's a corresponding stable range where the groups are all going to be the same. And we observed this in the case of S pi n plus 1 of Sn. I mean, we wrote down explicitly what this range was. All right, so as I observed before, we're interested in understanding motivic homotopy sheaves, and to understand Murthy's conjecture, we're going to need to know not just the primary obstruction, which was given by Fabien's theorem, but also a secondary obstruction. So we're going to need to know something about the next homotopy sheaf of An minus the origin. All right, so here's where there's a problem that arises. So Morel actually established an exact analog of this statement in motivic homotopy theory for S1 suspension. All right, but remember, there are two circles here. In our algebra geometric situation, because an plus 1 minus the origin is P1 smash an minus the origin, we really need to understand what happens with respect to P1 suspension. So one way to think about that would be to first do something for S1 suspension and then try to understand what happens for GM suspension. But unfortunately, it follows from Morel's computations that the Freudenthal suspension theorem is false for just GM suspension without some suitable hypothesis in place. So you can just compute, if you just take the simplicial circle and you compute its homotopy in degree n, you just get Z, where if you take the GM loop space on Sn smash GM, you can compute its nth homotopy sheaf and you get Milnor-Witt K0, which turns out to be the Grothendieck-Witt ring or the unramified Grothendieck-Witt sheaf. And that's not Z if I'm, say, working over a non-algebraically closed field. All right, so Jean and I basically use low-dimensional exceptional isomorphisms of algebraic groups to try to compute some of these homotopy sheaves of an minus the origin. And so we studied these for small values of n, and based on those computations for small values of n, we made this conjecture. The precise form is sort of not going to matter so much, but what's important is that there is some sort of regularity here for various n. So this Grothendieck-Witt sheaf that appears on the right is something that comes from the unit map for orthogonal for Hermitian K theory, and this K Miller n plus 2 mod 24 is coming from some sort of motivic Hopf map. All right, so our unstable conjecture was based on a number of things. So P1 stably, this becomes a conjecture of Fabien Morel. And when I initially wrote this, I think Kyle and Paul Arna had established versions of this conjecture of Morel, at least upon taking sections over some fields. And then later in kind of a tour de force computation, Oliver Rondigs, Marcus Spitzbeck, and Paul Arnostvar established this conjecture of Morel. So in particular, they established the stable analog of this, this conjecture. And unstably, earlier I showed you that there was a difference between the homotopy pi r of SR minus 1 for various values of R. For very small values of R, the answer was different. And the situation in algebraic geometry is similar. Our answers for n equals 2 and 3 for this relevant homotopy sheaf are a little bit different. For example, for n equals 2, this 24 becomes a 12, and there's some additional factors that correspond to things that happened over the real numbers, for example. All right. So we can't, I mean, we can only expect this kind of uniform situation for sufficiently large n. All right. So how does this bear on Murthy's conjecture? Well, Murthy's conjecture follows from the following fact. So if n is an integer which is bigger than or equal to 3, and k is a field which has characteristic 0, then we can consider the unit map of the P1 loops P1 suspension adjunction. And this actually induces an isomorphism on homotopy sheaves in some explicit range. Now, the actual theorem is more general than this, but I stated it like this to have to introduce a minimal number of hypotheses. So what the observation here is that there is a range in which the P1 stable homotopy for sufficiently nice spaces actually computes the unstable homotopy. And this is fantastic because it tells you that you can, I mean, stable things are computable. And so there's a host of technical tools, various spectral sequences for computing in this stable range. You can make those computations, and then you can use this result to destabilize them, get an unstable computation. And the unstable computations are the things that have bearing on geometry. So we were in this weird situation in motivic homotopy theory where you knew how to do stable things, but you didn't know what their relationship to the unstable world was. And so this theorem provides an explicit link between the two. All right, so I have 4 minutes left, and I'd like to sketch the proof of this theorem. So what's the idea? Well, earlier I tried to emphasize that S1 suspension somehow played a distinguished role. And I think that's an unfortunate accident. So basically what we do is we try to introduce a refinement of the classical Postnikov tower, which keeps track of GM connectivity as well as simplicial connectivity. So we want to basically treat both spheres on the same footing. So one way to build the classical Postnikov tower is to nullify spheres. In other words, localize the projection map from a suitable sphere to a point. So that's what we do here also, except now we're going to nullify the GM circles or their various suspensions. So we introduce these notions of GM n equivalences, where we, so they're the maps that are generated by this set of maps, and we Gauss field localize at these things. So this introduces a notion of GM connectedness. We'll say that a space is GMN connected if it's equivalent to its Gauss field localization for this particular functor, and GMN truncated if its localization is a point. All right, so this is a completely formal definition, and what actually makes it useful? Well, before I say that, let me just say that this introduces a bi-graded notion of connectivity. So PQ connectedness means what you might think it does. From the definitions, it's not hard to tell when a space is truncated. And for example, Vygotsky's motivic Allenberg plane space KZ of n2n is n-1, n-1 connected and GM n truncated. So basically what this means is that if I take the n+1 fold GM loop space of this thing, I get something contractible. All right, so what makes this actually work? Well, there's been recent work of Tom Bachmann and Maria Jakobsen, supplemented by some work of Tom Bachmann. And the basic observation is that under the presence of some GM connectedness hypotheses, the Postnikov tower can be refined in the following way. So the Postnikov tower is some tower of fibrations, and there are K invariants, which are the things which tell you how to build that fibration. And those K invariants typically take values in some sort of Eilenberg plane sheaf. And that sheaf is only, in some sense, S1 stable in general. And so what Bachmann and Jakobsen observe is that or suitably translated, is that under some GM connectedness hypotheses, those K invariants actually arise from maps to P1 infinite loop spaces. So this is sort of the fundamental difference between the classical story and what we're doing here. All right, so what we can do then is reduce the case of P1 Freudenthal to the explicit case of KZ of n2n. And now this ends up being a bit of geometry. So I'll just put it up since I'm out of time, but these are the main ingredients in analyzing the connectivity of the Freudenthal suspension theorem for KZ of n2n. First, the identity map on KZ of n2n factors through the unit of the loop suspension adjunction and the assembly map in the motivic Allenberg plane spectrum. And it ends up being sufficient to analyze the connectivity of the assembly map. And that's something which is pure geometry. Because of Vygotsky's motivic Dold-Tom theorem, the motivic Allenberg plane space is a colimit of symmetric powers of suitable spheres. And that symmetric power of spheres is built, the assembly map is built from some representation theoretic gadget involving actions of the symmetric group on affine spaces, as I've indicated here. And so if I want to understand the fiber of the connectivity of the assembly map by a Blaker's Massey style result, it suffices to understand the cofiber. And the cofiber can be described absolutely explicitly as some Tom space of some vector bundle. And you can just stratify the variety on which this vector bundle lives and kind of build up the connectivity of that cofiber. This is not an unprecedented argument. The ideas go back to Nakaoka in his analysis of the symmetric group and Vygotsky's paper on the zero slice of the sphere spectrum. And so, I mean, maybe this version of Nakaoka's results are in work of Aron and Dwyer on partition complexes, but it's sort of something that's been studied in homotopy theory since the 80s. So in any case, at the end of the day, we can now compute stably and deduce unstable phenomenon. And I hope this is something that has lots of applications for torsors beyond vector bundles. And anyway, let me quit there.
Are there any questions?
I'll jump in with a basic one. Thanks for that excellent talk, Aravind. You may have mentioned this in passing, the GM Freudenthal is false in general. That 0th Milnor-Witt K group is the integers over a quadratically closed field. So is there a version that's true with some sort of algebraic closure hypothesis, or is it still false?
So I guess I should be a little bit more careful about what I mean by false. I want these things to be isomorphic as sheaves. So that's the issue. So
Gotcha.
even if your base field is quadratically closed, you can find, you know, some extension, some finally generated extension of it where the Grothendieck-Witt group will not be Z.
Thanks.
Sorry, I have a small question. So in the beginning, you said there is a fiber sequence over with Grassmannian, yes. Somewhere in the beginning, you said that the base should be a perfect field or the Dedekind domain, and so it doesn't. Yes, this is it. So it doesn't generalize, or does it? Should it generalize?
It's equivalent to knowing the Basque-Bullian conjecture for all smooth K algebras. So anytime you know the Basque-Bullian conjecture for all smooth K algebras, then you get this fiber sequence. And it's, I think the Basque-Bullian conjecture for all smooth K algebras is only known in exactly these cases. I think there's been recent results which, yeah.
Any other questions?
I'll jump in with one more. The GM connectedness has a similar flavor to the slice construction and stable motivic homotopy. Is that the right intuition? Kind of where...
Absolutely, yeah. This is a destabilization of it, and that actually is a good opportunity. I think the unstable version of slice constructions was built by Pablo Pelaez. This was related to this Sujata birational localization construction. So Pablo sort of inverts a different class of maps. He inverts the maps which are dense open immersions with codimension bigger than or equal to D complement. I think this is closely related to his construction in that case. We just localize it a simpler class of maps. It's better for our controlling our Postnikov tower, for example. But absolutely, I mean, effectivity conditions are exactly the way you should. That's the way we think about it also.
Okay, very cool. Thanks.
Any other questions? Well, if there are no other questions, let's thank the speaker again.